In this class, we're going to introduce the whole notion of thermochemistry. Now, I think if you listen to the title, Thermochemistry, thermal, heat, chemistry, reactions. So if we take the word thermochemistry and break it into everyday English, it's the study of heat energy during a chemical reaction. Okay. Now, in order to, I suppose, introduce this fully, let's go back to junior cert. And I hope in junior cert at some stage you heard the words endothermic and exothermic. Now, just in case you didn't, I'm going to explore those first. Take that stove that we have here in the slide. The reason why we light a stove is in order to get the fuel, be it the coal or the charcoal or whatever is burnt inside, to give energy out into the room to make it feel warmer. Okay? Any chemical reaction that involves heat traveling outwards from the reaction itself is called an exothermic reaction. Now, an exit is a door outwards. Exo always means outwards. So exothermic means heat outwards, or the outward flow of heat. Okay, so therefore an exothermic reaction in chemistry is very, very easy to distinguish because they always feel warm to the touch or hot to the touch. Okay, they radiate heat, so they actually radiate energy and they feel warm to the touch. All right, so burning fuels, for example, seeing that we're on that topic of fuels, burning any type of fuel always produces heat, and that's why it's called an exothermic reactions. They're hot to the touch, and there are many of them. For example, striking a match. You strike a match, as soon as the sulfur begins to burn, it liberates heat. A burning candle, okay? The gas on your stove. All of that is a chemical reaction, involves the outflow of heat, so therefore they're all exothermic reactions. I'm sure you can think of various others as well as you think of everyday life and where heat is given outwards. When we talk about the opposite, the flow of energy into an object in order to bring about a chemical reaction, okay, that's where we call it an endothermic. So endo, like entrance, means going in. So anything beginning with endo is internal, it's inwards. So exo is out, endo is in. So when we have a flow of energy moving into a system, the energy is normally needed by the system to bring about a chemical reaction. Typical example is the top picture you see there. When you open an egg and you open it onto a hot frying pan and you watch it, it goes from being clear jelly into a very, very solid white, what we call white protein, okay? And then the yellow, which is the center of the egg, or the yolk of the egg, again goes from being yellow and runny into being solid. Chemical reactions are taking place there that would not take place if you didn't heat the egg in the first place. So in this case, we've got an inward flow of energy, bringing about a transformation in the proteins of the food, making it edible and safe for us to eat. The second, and probably the most important of all endothermic reactions, is photosynthesis, where you have the green chlorophyll absorbing the energy from the sun to bring about the chemical reaction of locking carbon dioxide and water together to give a simple starch which acts as food for the plant, and then, as you can see, life-giving oxygen gas. So that's probably the most important endothermic reaction. And again, I'm sure that you can think of many other places where energy flows inwards in order to bring about a chemical reaction. Okay, but keep in mind what the term is. The term is they are endothermic reactions. So exothermic is when a reaction gives out heat. Endothermic is when it takes it in order to bring about some type of chemical change. If exothermic reactions are hot to the touch, then endothermic reactions will normally be cool to the touch. One very popular endothermic reaction that some of you never thought was an endothermic reaction is sherbet. You know, the fizzy powder. When you put fizzy powder into your mouth, the actual temperature of your mouth drops by several degrees as the energy from your mouth is taken to bring about the chemical reaction that liberates the fizzy carbon dioxide. So there's another endothermic reaction, okay? And there is a chemical change taking place because you're creating carbon dioxide that wasn't there in the first place. So when we talk about the heat of a given chemical reaction, we're talking about the change in heat. Now, some reactions are exothermic, which means they pump out energy. Others are endothermic, which means they take in energy. And if I was to be properly chemically correct, I would kind of say that chemical reactions are both. Okay, they're both endothermic and exothermic. What makes them, by definition, endothermic and exothermic is the excess. If they give out more energy than they take in, or if they take in more energy than they give out. Okay, and we'll explore this a bit more in a few moments. But I do want to just pause for a moment and tell you, in this chapter, the most important thing that you will have to learn, and I mean learn, are the definitions that I'm going to give you. Because the definitions that begin here now with the heat of reaction, they're going to form the basis for the mathematical application of thermochemistry in Hess's law. So as I give you definitions, please make sure that you learn them before you come back to the next module, the next lecture, so that you understand exactly what we're talking about and you can see how these definitions are used in future calculations. So what's the heat of reaction? The heat of reaction is the heat change that takes place when a chemical reaction proceeds according to its balanced equations. Now, if we go back to the beginning of fifth year, one of the things that we did early on was we looked at how chemical equations must always obey the law of conservation of mass. Okay, so therefore, whatever number of atoms you have in the beginning, that is the number of atoms you must have at the end. I.e., whatever mass of reactants you have at the beginning, you must also have that mass of products at the end. What happens is that energy is needed to break bonds, and energy is released when new bonds are formed. And it's the difference between the energy needed to break bonds and the energy released when bonds are made that gives the reaction its title of being endothermic or exothermic. So therefore, a general definition, and the most general basic definition of thermochemistry, is the heat of reaction. It is the heat change that takes place when a chemical reaction proceeds according to its balanced equation. That is a very, very important definition, which I'm going to mark NB, because that is something that you do have to learn off by heart. Okay? So take this reaction here. Hydrogen in the gaseous form plus oxygen in the gaseous form gives water in the gaseous form. Now look at this unusual symbol here. This unusual symbol is what we call delta H. Delta means the change. Okay? So therefore the change in heat is minus 242 kJ mole minus 1. Now I've got to explain all this as we move on. First of all, we have 1 mole of hydrogen gas and a half a mole of oxygen gas, giving 1 mole of water in the gaseous form. The change in heat is minus 242. Now I want you to think about something. When your bank account goes down, when your bank account is going down and down and down and down and down in terms of its balance, money is being withdrawn. Money is going out of your account. So therefore, in chemistry, when the energy is negative, it's being lost to the universe, or it's being given out to the universe, which means a negative symbol is always going to be an exothermic reaction. So I can read this as the production of water from hydrogen and oxygen gives out 242. Now what's kJ? Well, a joule, Joule, that is a unit of energy. K stands for the same thing it stands for in maths, 1000 kilo. Okay, so this one here is minus 242 kilojoules, mole to the minus 1. That just means per mole. All right, minus 242 kilojoules means that I have lost 242,000 units of energy by burning 1 mole of hydrogen with a half a mole of oxygen. All right, that's a lot. That's a lot of energy. So minus 242, that means a kJ means 242,000 units of energy given outwards. So therefore, whenever I burn hydrogen and oxygen, I expect the reaction to feel hot to the touch, and it is. It is the chemical reaction that gets spaceships up into space, outside the Earth's gravitational pull. Okay, so that is what the solid rocket boosters are made of. Solid hydrogen, solid oxygen coming together, being burnt, giving huge amounts of energy that give thrust to the machine to get it outside the Earth's gravitational field so it can go into orbit around the Earth. Okay, so there's quite a lot of detail in those particular equations. Next one, CH breaks down into C and H, and let's call it properly. So CH, carbon hydride, breaks down into gaseous carbon and gaseous hydrogen. And delta H for this reaction, this time is plus 335 kJ per mole. Now what does that mean? That means here the change in heat is an inward flow. Think of your bank account. If your bank account is going up positively, money is flowing in, correct? So if money is flowing in, your bank account is adding up So therefore the addition sign means energy inwards. So this means that as this reaction takes place, we have a change in energy which is represented by an inward flow of 335,000 units of energy for every mole of carbon hydride that is broken down. Okay, so I want you to think very carefully of what the symbols mean. That's all I'm really interested in here. The negative symbol means an outflow of energy, decreasing bank account. Think of it that way, it's an outflow of money. And this one here with plus is an inflow of energy, increasing the energy content of the reaction. Think of it in your bank account. If your bank account balance is going up, money is flowing in. Okay, so just think of it that way so you don't get confused between the positives and the negatives. Okay, second definition, and again something of immense importance. The heat of combustion. First of all, I hope everybody understands what combustion is. Combustion is when you burn something in oxygen. Now, chemically speaking, all burning does not necessarily have to give a flame. At the moment, as you sit there listening to me, you are chemically burning the food that you ate for your breakfast or your lunch or your dinner or your tea, okay? But you're not bursting into flames. Now, there is a lovely thing called spontaneous human combustion, which you can look up in your own time, which is a phenomenon where bodies have burnt into flames and burnt, and anything around them hasn't burnt. You can look it up on Google. It's true. It's a phenomenon. Happens. But usually, the human body is able to burn food slowly, release the energy slowly, with no sign of a flame. That's still combustion. So combustion is mixing something with oxygen. Sometimes, if it's vigorous enough, you'll get a flame. If it's not vigorous, then you won't get a flame, but you'll get a slow release of energy. Okay, so just think combustion is mixing something with oxygen to produce energy. So there's a definition behind this, and this is your second definition that you are going to have to learn. And here it is. The heat of combustion of any substance is the energy released when 1 mole of any substance is burnt in excess oxygen. Or to put it a more general way, the heat of combustion of a reaction is the heat change that takes place when 1 mole of a given substance is burnt in excess oxygen. Now keep in mind, the mole is the way we talk about quantities in chemistry. We don't talk about a kilogram, we talk about the mole, okay? So listen to the definition again. The heat of combustion is the heat change that takes place when 1 mole of any substance is burnt in excess oxygen. Burnt meaning its energy is released. Okay, it doesn't have to necessarily give you a flame, but its energy is released. So there's your definition, and that is something that you have to remember. 2 things in this definition are very important. They're highlighted in red. First of all, it's the heat change that takes place when 1 mole of a substance. You can't use any. Don't use a half a mole. You don't use 3 moles. 1 mole of a substance is burnt in what? In excess oxygen, because it has been shown that if you reduce the amount of available oxygen, you get different products. Take, for example, carbon. If you burn carbon in plentiful oxygen, you get carbon dioxide. If you take carbon and you burn it in restricted oxygen, you get carbon monoxide. Hence the reason why we have all those tragic accidents in mobile homes where there's not enough oxygen to mix with the gas that's being burned, and therefore carbon monoxide is produced instead of carbon dioxide, and people are killed quite quickly because it's an absolutely lethal gas. Okay? So the amount of oxygen is important. So if we want to get the heat of combustion of a substance, we have to make sure that oxygen is always in excess. So here's the definition one more time. It is the heat change that takes place when 1 mole of a substance is burnt in excess oxygen, or completely burnt in excess oxygen. So I want you to take this equation here. Carbon in its solid form and oxygen gas react together to give carbon dioxide gas. Delta H, the heat change for this reaction, is minus 383 kJ mole minus 1. Now what does that mean? That when this reaction takes place, when 1 mole of carbon is burnt in a proper amount of oxygen, 383,000 units of energy are released to the atmosphere. So it's going to be a hot reaction. This is the same as burning coal at home. Coal is carbon. Okay, you get a decent amount of heat from 1 kilogram of coal. So you get a decent amount of heat from a mole of coal. All right, or a mole of carbon in this case. Watch the following reaction. This is not the heat of combustion, and I hope you can see why. We are burning a mole, so that's satisfied, but we have reduced the amount of oxygen. And instead of getting carbon dioxide that we should get, we're getting carbon monoxide, which is a sign that the oxygen has been limited. So therefore, we're not taking into consideration the proper definition. 1 mole of a substance burnt in excess oxygen. So if the oxygen is not excess, that figure there is not the heat of combustion. It is the heat of the combustion of carbon in a restricted flow of oxygen, which is not what we're looking for. And again, you'll notice that the energy is much, much lower. It's only 111,000 units of energy given out to the atmosphere when you restrict the oxygen. And most importantly, carbon monoxide is made instead. Okay. What about this one? 2 moles of C4H10, MEPB, butane, good, and 13 moles of oxygen react to give 8 moles of carbon dioxide with 10 moles of water, and the energy change is 5,720,000 units of energy. That's 5 million. Okay, it's massive. What? Given out to the universe. So this is a very hot reaction. But is this figure the heat of combustion? Well, take a look. What's the heat of combustion say? It is the heat change that takes place when 1 mole is burned in excess oxygen. Is the oxygen in excess? Yes. 13 moles of it. Is 1 mole of MEPB butane being burned? No, it's 2 moles. This is not the heat of combustion. What I would have to do there is I would have to take minus 5270 and divide it by 2. So 5720 divided by 2, which would give me the proper figure of minus 2860. And that would be the heat of combustion. Okay? So keep in mind, there must be 2 criteria if you want the heat of combustion. 1 mole of a substance burnt in excess oxygen. Okay. How do we measure it? So how do I measure the heat of combustion of butane, for example, as being minus 2,860? How did I get that? And the answer is we do it by experiment. We've got to take these fuels and put them into what's called a bomb calorimeter. Now, it's not a thing that explodes, okay? So you're not going to be worried about an explosion in the lab. It's not. It's a bomb calorimeter. It burns the fuel. It allows the fuel to release its energy by burning it in excess oxygen. But the energy that's released is transferred to a surrounding body of water. And the increase in temperature of the water is recorded, and by a mathematical formula is turned into what we would say the heat of combustion of that substance is. Okay. Now, what does the bomb calorimeter look like? Well, there it is. And I just want to point out a few things on the bomb calorimeter. First of all, this thing down here, that's the bomb. Okay. Because in there we have a plentiful oxygen supply. That's extremely important. It has to be plentiful. And we have the substance that we're going to burn in a little crucible. Now, a crucible is a porcelain dish that is able to withstand very, very high temperatures. So we put the sample in there and we allow the wires then to come in here in order to burn the sample. And because the sample is burnt in excess oxygen, it will be completely burned. Now, how much do we put in there? Well, obviously, you're not going to put in a mole because a mole might be too much. So you're going to put in a known quantity. All right, so say 10 grams, because you can always bring it up to 1 mole when you're finished. You can always do mathematics on it to extrapolate it back up to what you require. So in this case here, you put your sample under test in the crucible. You surround the crucible with an excess supply of oxygen. You screw on the lid. You put in the 2 electrodes, I should say, which will deliver the charge to burn this thing. And when you burn it, the heat will move outwards into the water like that. It'll go out into the water, raising the temperature of the water by a number of degrees. So what we have to do with our thermometer is we have to take the temperature before and after we burn the food. Okay, so you take the temperature before, you mark it down as something degrees Celsius. You then take it after as y degrees Celsius, and you get the change in temperature by subtracting the 2. That temperature is produced by, say, 10 grams of the fuel. So you can easily then, by a simple mathematical formula, find out, well, how many degrees would I expect if I was using 1 full mole? And then that will give you what we would call the heat of combustion of that particular substance. Okay. Now, you're lucky because I have a nice animation lined up down here. And this animation allows you to see how the bomb calorimeter works. I'm going to demonstrate this once, and then I'm going to let you play away with that video. If you click that link there, if you click that, it'll bring you to the following site. So just allow me to bring that down for a moment. And let me go back here. There's me. Let me go back to this site here. Okay, so here we have a bomb calorimeter. Here we have our bomb, plenty of oxygen, and here we're going to put in our samples. Okay, salmon, cheese, hamburger, plums, Fritos. Now, Fritos are Doritos over here. That's the American version. Tomato, cantaloupe, and broccoli. All right, so what I'm going to do, notice that all their masses are different. I'm going to take, say, It's 56 grams of cheese. And I'm going to move the cheese from there, take it, and put it in if I can. Come on, cheese. If I can get the cheese to go in. Oh, it won't go in. Maybe I might go in with this. No. Okay, this is my cantaloupe.
A current ignites the sample.
Bang.
The temperature change tells us the heat released.
See that?
1 calorie raises the
maths.
temperature of 1 kilogram of water by 1 degree.
Okay, that's fine. That's brilliant. But you notice what happened? We started at 22, we went to 29. So therefore, the mass of cantaloupe that we actually burned, which is watermelon by the way, which we burned, has raised the water by 7 degrees. So what we're going to do is then we're going to bring the amount of food back to 1 mole and see how many degrees Celsius would I get from 1 mole of that particular food stuff. Now you can play around with this yourselves. You can have fun with it because there's plenty of others there if I just go through this.
The density of water is 1 kilogram per liter.
That's just waffle. Come on, up you go.
5 liters of water weighs 5 kilograms.
Okay, we don't have to know.
Multiply the temperature change times 5. The answer is the number of calories in the food.
Okay, very good. So now that we know how to measure the heat of combustion using a bomb calorimeter, we've got to ask ourselves why it's important. Why do we need to know the energy content of given foods or given fuels and so on? And the answer is because we want to compare their efficiencies. Okay. Now, if you go back to that animation or that simulation that you were playing around with, where you were burning tomatoes and you were burning plums and you were burning cheese and you were burning tuna and Fritos and all these kind of things, you'll notice that different quantities gave different temperatures. So we couldn't really compare how efficient one food was as a fuel in relation to the other by using the masses that were given. What scientists do is they conform on one mass, and that is the kilogram. Okay, so when they have a kilogram of food burned and they measure the release of energy from that particular food for 1 kilogram of that food, that is what we call the kilogram calorific value of that food. Okay, so we're kind of getting into nutrition and dietetics and so on. So if you take a kilogram of any food and you burn it in excess oxygen and you measure the amount of calories that come from it, that's the kilogram calorific value. Now, as you can see from the bomb calorimeter, the crucible is too small to hold 1 kilogram. So therefore we can vary the mass. So if I burn 10 grams of a certain fuel and get a certain number of degrees Celsius as a rise in temperature, I can multiply that by 100. And that will give me 1 kilogram. So all we've got to do is burn a known amount of food in the bomb calorimeter, see how many degrees we get for that particular number of grams, and then bring it up to 1,000 to get the kilogram calorific value. Okay, and the kilogram calorific value is a way that we can compare the efficiency of foods as fuels for the human body. That's exactly what it is. So chemists sometimes relate to the heat given out by a fuel in terms of its mass content. Okay, mass fuel content. For example, we might say 100 grams of cornflakes will give out, see the minus symbol, will give out 1,550 kilojoules, which is 1,550,000 joules, or units of energy, whereas 500 grams of petrol will give out 24,000 units, or 24 million units of energy per 500 grams. So therefore, we can't compare these two unless we standardize both of them up to a kilogram. So what I could do here is I can multiply that by 10, and that's going to give me minus 15,500 kilojoules. And then I multiply this one times 2, which is going to give me minus 48,000 kilojoules, okay, per kilogram. But because both of them are now in terms of a kilogram, we can now see efficiently which one of these fuels is better. And we can see petrol obviously is better than the cornflakes. So therefore, in the morning for your breakfast, have a bowl of petrol and you won't have to eat for the rest of the day. Okay. So that's why we have to use the kilogram. Okay, just in case you're wondering. So standard mass of the fuel that is under test is a kilogram. It doesn't mean we have to burn a kilogram. It means that we can burn a known mass and bring it up to a kilogram to see how many degrees Celsius would the water rise if I was to burn a kilogram of this particular food. A known mass of fuel is burned, as we said, in the bomb calorimeter. When we work out the energy released by 1 kilogram of fuel, what can we do then? We can put them into a hierarchical order, which ones are the best foods for energy content, which ones are the worst foods for energy content. And if you go back to the foods that we had in the bomb calorimeter, we had things like plums, which would be high water content. Okay, then things like cheese, which would be very, very high fat content, and then of course the Doritos down at the bottom right, which would have a very high oil content. So it'd be fun to go back, maybe as an exercise, see how many grams of each you're burning in the bomb calorimeter, record the rise in temperature for each food, then bring them all up to 1 kilogram and see which one of those particular foods gives the most fuel per kilogram. Get the kilogram calorific value for each of those foods in terms of degrees Celsius. Let's make it easy for yourselves, okay? So go back to the animation, burn all the foods, write down what each mass gives in terms of a rise of temperature, bring each mass up to 1,000, see how many degrees Celsius you get per kilogram, and then see which one of the foods is the one that releases the maximum amount of energy per kilogram. Okay. So the kilogram calorific value, as we already said, it's the amount of energy that is released by 1 kilogram of a given fuel, okay? And the bomb calorimeter is the way in which we will measure that particular output of energy. The energy output of fuels, therefore, is determined by, as I said, their kilogram calorific value. What does that mean? The amount of energy released by 1 kilogram of a given food. Now, we don't burn it. I've said this to you already 3 times. You don't burn a kilogram. What you do is you burn a certain known amount of food and you bring it up to 1 kilogram and extrapolate out how many degrees Celsius the water would rise through if 1 kilogram of that particular food was burnt in excess oxygen. We use this number then to compare, as we said already, the efficiency of fuels, or in this case, the efficiency of foods. Which one of the foods in that simulation had the highest energy content? So therefore, which one of those fuels would be the one that, or foods, would be the one that we would take in the least amount? Okay, because don't forget, the higher the energy content, the higher the calories. The higher the calories, the more inclined the body is to turn those calories into fat, shove them under the skin and increase the body mass. So we don't want too many blocks of cheese for breakfast. We certainly don't want too many bags of Doritos for breakfast. So again, we've got to make sure our diet is balanced so we don't overdose on energy, which is quite a possibility too. So just to finish this, there's one other way that we can work out the energy that is created or taken in by a given chemical reaction. And that's by looking at what we call bond energies. Okay, now just to summarize this, bonds, I'm talking about chemical bonds. And there are 2 things we can do with chemical bonds. We can create bonds between atoms and we can break bonds between atoms. Now, as the picture down here suggests, energy is required to break bonds. Now, if energy is required to break bonds, then the opposite is also true. Energy is released when we make bonds. So energy is required to break them, energy is released when we make them. So what's a chemical reaction? A chemical reaction is nothing more than bringing the reactants together, breaking all their bonds, getting the individual atoms to recombine into products by forming new bonds. So therefore, energy has to be inputted to break bonds, and energy will be released to create bonds. So therefore, as I said to you at the very beginning of this class, every chemical reaction is both endothermic and exothermic. However, what defines it is which one of those 2 is in excess. Okay, and I'm going to demonstrate that by an example here. So let's look at the combustion of methane. Methane, you know, is the very first member of the homologous series that we call the alkanes. 1 carbon, 4 hydrogens. When I burn methane in excess oxygen to produce carbon dioxide and water, the heat change has been measured accurately to be minus 890 kilojoules per mole. Now, what does all that mean again? When I take 1 mole of methane in excess oxygen, the reaction will give out 890,000 units of energy. So this is going to be quite a hot reaction. This is going to be an exothermic reaction. But where did they get that figure from? Well, maybe they took methane in a crucible, burnt it in a bomb calorimeter, and got the measurement that way. That's a possibility. However, methane is a gas, so there'd be a bit of a difficulty trying to burn a gas in a crucible. Anyway, let's let them worry about that, not us. But that's one way we can do it. The other way we can do it to get an approximate value is to look at the bond energies. Now, what do I mean by that? When you bring together methane and oxygen, what you have to do is you have to break all the bonds of methane and break all the bonds in oxygen to create individual atoms, like a Lego set. Then you take the individual atoms and you rebuild the CO2 molecules and the two H2O molecules. Same number of atoms on the left-hand side, same number on the right-hand side, same mass left and right. Law of conservation of mass is always followed and obeyed. Okay, so in this case, we're going to break 4 CHs, we're going to break 2 O2s, and we're going to make 2 COs and 4 OHs. Now, where am I getting all this from? Let's go a little bit more into detail. The reaction proceeds because bonds in the reactants are broken, that's on the left-hand side, and bonds are made in the products on the right-hand side. So energy is needed to break, energy is released when we make. Who needs the greater amount of energy? Do we need more energy than we release, or do we release more energy than we need to break the bonds? Based on those figures, that'll tell us where something is exothermic or endothermic. Energy, as I said, is needed to break bonds. That picture will help you to remember that. And energy is released when bonds are made. So therefore, this is true for all chemical reactions. So no matter what chemical reaction you're doing, energy must be put into the system to break all the bonds. And then when all the individual atoms come together and start to reform new bonds, energy is released. So our question is, who's the greater? Is the demand of energy greater than the release? Or is the release of energy greater than the demand? And that is something that bond energies will help us to see. So I want to take an example here. Delta H is the difference between the energy required to break the bonds and the energy released when we make the new ones. So in this reaction, the burning of methane and oxygen to give carbon dioxide and water, we have an accurate figure of minus 890 kilojoules per mole. Okay, where does that come from? Well, let's take a look and see. Here is CH4. Do you notice there is 1, 2, 3, 4 CHs? Okay, so go down here to the table of energies that we have. There are 4 of them. Okay, here there are 2 O2s, so there are 2 of them. All right, so they all have to be broken. So in breaking those, that means that we need 413, which is multiplied by 4, and we need 495, which is multiplied by 2. Now go over the other side. I am creating a C double bond O there and a C double bond O here. So I'm creating 2 of them, and because I'm creating them, that means I'm releasing that energy. And also, I'm creating an OH there, 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 and there. So I'm actually creating 4 of them, which means that will be released 4 times. So let's do this. 413 multiplied by 4 works out as minus 1642. 2 times, oh, that's plus, isn't it? Sorry, apologies, because we're breaking those. 2 times 495 works out as plus 990. So in other words, those 2 figures represent the amount of energy needed to break all bonds in the reactants. Now, let's take 2 times minus 745. That's 1490. So that's minus 1490. So that's going to be released when we make 2 C double bond O's. And then 4 times OH is 4 times 467, which is minus 1868. So that there is the energy released. And from this very simple calculation, if I go to the last slide, here's what we notice. 4 CHs are broken. That means we need, that's the pluses in there, we need 1652. 2 O double bond O bonds are broken. So that means we need 990. Altogether then, that means that we require 2642 kilojoules of energy to break those bonds. Okay, what about the energy released? We create 2 C double bond O's, which means we release 1490 kilojoules of energy. And then we also create 4 OH bonds, which means we release 1868. So altogether, the energy that's released is 3,358 kilojoules. So that's the energy required to break all the bonds. That's the energy released when we make the bonds. So you'll notice there is an excess of energy released to the system. So this is most definitely going to be an exothermic reaction. And in fact, from these very simple calculations, we notice that there's an excess of minus 716 kilojoules of energy, which means 716,000 units of energy have been released. So this is going to overall be an exothermic reaction because the release of energy is greater than the energy required to break all bonds. Now, there's not much of a reference anymore in the exams to bond energy. Okay, bond energies have kind of disappeared. All we need to remember is the following. Energy is required to break bonds. Energy is required to make bonds. If there is a greater amount of energy required than released, it's endothermic. If there's a greater amount of energy released than there is needed, it's an exothermic reaction. And those two categories are the only two categories that exist for all chemical reactions in terms of thermochemistry.